Hi, for this video, we'll be talking about projectile motion. Now, what is projectile motion? Projectile motion is actually just a combination of two kinds of motion, which is uniform horizontal motion and free fall. So when we say uniform horizontal motion, the velocity of an object does not change all throughout the course of the motion of that object. While of course for free fall is an idealized motion where the object is only influenced by the force of gravity or the acceleration due to gravity. Now, these two components of projectile motion are independent from each other. And since they are independent, then the individual characteristics or features of these two kinds of motion will apply to projectile motion. We can also describe projectile motion as an object that is moving along both in the x and y axis, which can be launched horizontally or launched at an angle with respect to the horizontal. Now, when we look at the illustration here, this is a projectile motion, and you have two terms, trajectory and range. Now, trajectory is the curved path of the projectile. So if this is the object, which is moving along that curved path, and that curved path or the path that the object takes when it's moving, where the motion is a projectile motion, then that's a trajectory. Then range will be the horizontal displacement from the initial position of that object to the final position. That is the range, or basically just the displacement along the x-axis. Of course, when we speak of the y-axis, you have heights at different points. And this one here, since this is also free fall, then this is your maximum height. So h max. Oops. H max. So let's move on. Now, digging deeper or looking further into the components or the features of a projectile motion. So let's take a look at this illustration. So we have here 5 points: point A, point B, point C, point D, and point E in our projectile motion. Remember that a projectile motion both has your uniform horizontal motion, where acceleration, remember that's x, is equal to 0 because the velocity does not change along the x-axis. But for your y-axis, then it's influenced by the acceleration due to gravity, which is your negative g, or negative 9.8 meters per second squared, right? So looking further or looking into these points here, this is a projectile that is launched at an angle with respect to the horizontal. So this is the initial velocity of the object, which is launched at an angle. Therefore, this is your theta, so you can see there. Now, since this projectile motion, again, has its x and y component, then we can resolve this initial velocity into its x and y components. Therefore, you have initial velocity in y and initial velocity in x. Now, as it moves further in its path or in its trajectory, remember that in free fall, the velocity and maximum height along the y-axis will be equal to 0. If you remember our lesson in free fall, which is discussed as well in the previous video, that the velocity of an object on its maximum height in a free fall is equal to 0. It stops momentarily and then it moves down. But of course, for your x-axis, at any point here in the trajectory, your velocity in x will be equal because your acceleration is 0. Therefore, the velocity along the x-axis does not change. What only changes here is the velocity along the y-axis. As you can see here, this is your vector representation of the velocity along the x-axis, and it remains the same. It remains the same all throughout the motion of the object. However, for your velocity along the y-axis, as you can see here, you have a greater magnitude for the velocity in y-axis in point A, and then it gradually decreases because it's moving up until it reaches 0, and then it moves down, and then it builds up that magnitude again. Okay, and again, to remind you, projectile motion is only influenced by the acceleration due to which is moving down. Now, the actual position of the object that is moving along the projectile or along its trajectory at any given time is given by this kinematic equation, where your position in question is equal to the initial position plus initial velocity times time plus 1/2 acceleration due to gravity times time squared. Now, this is actually the vector sum of your displacements here, since this first one here, your V0t, this one, and this is 1/2 gt squared. So without, let's say there's no acceleration due to gravity, then the object will be having this motion or path. But since this is a projectile motion, it's influenced by the acceleration due to gravity, then there's a shift in that position. So this will be the actual position of the object. Now, since we're talking about your actual position along the x and the y, then we have these two positions as well when we talk about projectile motion, which is your range and your maximum height. What is range and maximum height? So as what we have mentioned earlier in this video, you have the total displacement along the x-axis, which is the range. So from the initial point of the object down to its final point along the x-axis, that's your range. So that's the x-axis. Now for the height, of course, at any point in the trajectory of the motion, there's different height, but the peak of the motion of the object is known as your maximum height, which is here at point A. Now, these are the equations which can be used to solve for range and projectile with only the initial velocity, the angle of projection, and your acceleration due to gravity as the known values. So your range is equal to your initial velocity squared sine 2 theta. This means you double the angle divided by g. And then the maximum height, or the height of the projectile, is equal to your initial velocity squared sine 2 theta squared, which means you square the value of that sine over 2g. Now, there's an important note here that these equations are only valid for symmetric motion, which means that when you look into the motion of the projectile, then they both have, or they are both the same in 1/2 of the motion of the object and on the other half. So as you can see here, if you take the half of that motion, they are the same. That's what is meant by symmetric motion. Now, how did we arrive at those equations? So let's look into how we derive the formula for the maximum range of a projectile. So of course, we start with a general 1D or one-dimensional kinematic equation. We still have the same illustration as the previous slide. Now, when we look into y, so our y is equal to the initial position plus initial velocity in y times time plus 1/2 at squared. That's your position in y. Now, since we know that your acceleration is equal to negative g, take note we are already factoring in the negative or the direction of g. So y is equal to y0 plus y0 y times time minus 1/2 gt squared. The substituting a with negative g, then of course your operations will also change because positive times negative, then you'll get negative. So you get 1/2 gt squared. So we already factored in the negative or the direction of the acceleration. Now what we're trying to do here actually is to try to solve first for the time, because remember that in projectile motion, the the motion of the object is influenced by the gravity. And by using your values along the y, you can actually solve for the time that the projectile is moving, or the object that the object is moving along its trajectory. And also, one good point to remember is that the time it takes for a projectile to reach its total displacement along the x will also be the time that it takes to reach the maximum, or the time to reach its position as well in y. So for example, here at this point, so this is your y and this is your x, right? The total time that it takes for this object to cover this displacement in x and to cover this displacement in y is the same. So or going back to our equation where y is equal to y0 plus initial velocity in y times time minus 1/2 gt squared, where our initial velocity is, or your initial position in y is usually 0, and y, or your total displacement, is equal to 0. Y is total displacement equal to 0? If we look at the projectile, so you have the object going up and then it goes down along the same plane, which means if you look at it, there's no change in position along the y-axis. Then therefore, the total displacement along y is 0. So substituting those values there, you have total displacement is 0, initial position is 0, then you'll get, or you're only left with v, or initial velocity in y times time minus 1/2 gt squared. Now, transposing your values, then you get, since you will have, you can get rid of that. And then if you transpose this one, then this becomes positive. So 1/2 gt squared is equal to initial velocity in y times time. So the time of flight is the time taken for the projectile to go from point O, or to point 0, to point B. Remember that we factored in the motion going up and going down. Therefore, the time here in our equation 1 is the time from point 0, or point O, to point B. So your point O time is 0 because that's the start of the motion of the object. Now point B, or to solve for the time in point B, we can rearrange the equation, which will, we can rearrange this equation, which will give us, if we try to rearrange that equation, we have 1/2 gt squared equals v0 along y times time, right? So how do we solve for just time? This is equal. So to solve for just the time, then we can separate the 2 times here because that's t squared. So if we leave one time there, or one quantity of, or one variable of the y, then that's v0yt over 1/2, or let me rewrite this on another side of the slide. So you have here, right, 1/2 gt squared is equal to v0yt. Now, of course, t squared is t times t, right? So if we just leave t in one side of the equation and transpose the other expressions, then you get v0yt over 1/2 gt, right? Because we separated this t squared to t times t, and we left the other t in one side of the equation. Then this can be canceled out. And this one here can be placed in the numerator as times 2. Then therefore, we get this equation where time is equal to 2 initial velocities in y divided by g. So that's your equation 2. And also, remember that we can solve for the component of the initial velocity. We can solve for, or we can further expand this initial velocity in y. Remember, this is your initial velocity and it has your x and y components. And this is your launch angle. Now, how can we solve for the x and y components of this initial velocity? So remember that the x component of that initial velocity can be solved using, since this is your v0x and it's the adjacent of the angle, then therefore what we can use is, what can we use as the trigonometric function? So if this is your v0x and you know the hypotenuse, so you know the adjacent and the hypotenuse, and what is the trigonometric function that uses the adjacent and the hypotenuse? So that is the cosine. So it will give you v0 cosine theta, or the launch angle. While for your initial velocity in y, this is your y here, so that is also equal to, or that can also be mirrored in this side, and that is now the opposite of your launch angle. And you know the hypotenuse, which is this initial velocity. So your initial velocity along the y can be solved using the value of the initial velocity times the sine of the launch angle. So if your initial velocity in y is equal to initial velocity times sine theta, then this can be further simplified or can be expanded into time is equal to 2v0, or 2 initial velocity times sine theta divided by g. So that's actually a formula to solve for the entire time of flight if the projectile is symmetrical, or the motion is symmetrical, and what you're trying to solve for is the time from this point to that point, given that your displacement along y is 0. Now, what we're trying to derive here is actually the formula for the maximum range. And this formula, this time formula, will be handy. So let's take note of that time is equal to 2 initial velocity times sine theta divided by g. So since the velocity in the x direction is constant, so now we look into the x component already, since maximum range is the x component. Now, the previous equation that we had was, remember, its time is equal to v2v0 sine theta divided by g. So just take note of that. Now, even though the values that we used in the previous derivation is values for y, again, remember that the time it takes for an object for its quantities in y will also be the same in x, or in its x component. So since the velocity in the x direction is constant, we use the range is equal to your initial velocity in x times time. This is from x is equal to velocity times time. Now, since your average velocity here, your velocity does not change all throughout the motion of the object, then therefore your average velocity will also be equal to your initial velocity. along the x, of course, since we are talking about x. And x is your range. That's why range is equal to initial velocity times time. Now, we substitute your equation 2, which is this one, to this equation. We know that the value for time, so if we look back to the previous derivation that we had, the time was the object going up and going down, right? Because we used values in y. But again, remember that the time it takes for the y, or the time it takes for the object to cover its quantities in y, will also be the same to cover its quantities along the x-axis. They will arrive at the same time, or it will cover its entire displacement in y at the same time its entire displacement in the x. So therefore, this time here is also applicable in the x component. So if we substitute that, then you get, of course, r is equal to v0x times 2v0 sine theta over g. Oops, there. So you just factor that in. Then you have, so what we used here muna is your v0y. So r is equal to 2v0x times v0y, or your initial velocity in x and initial velocity in y times time. Remember, this is also, your time is also equal to 2v0y over g, right? This expression here is also the same as this one. Let me write that one as a subscript so that you will not get confused there. So that's an equation for r. Now, if the initial launch angle, or your angle 0, measured with respect to the horizontal, then therefore your initial velocity in x will be equal to, as what I have presented to you in the earlier slide, that your initial velocity in x will be equal to v0, or initial velocity times cosine launch angle, and your velocity in y is equal to your v0, or initial velocity sine launch angle. Now, substituting these expressions, we know that the value for your initial velocity in x and the value for initial velocity in y is v0 cosine theta 0 and v0 sine theta 0 respectively. So if we substitute that, of course, this is your v0x and this is your initial velocity in y. Then that will give you r is equal to 2, of course, this is a subscript. Let me just correct that one. So v0, or initial velocity, times cosine theta, multiplied by your initial velocity times sine theta all over g. Now, since you have two initial velocities, then that's 2 initial velocity squared times sine theta times cosine theta divided by g. Now, we have here actually, if we will rearrange this one, you can actually get v0 squared times 2 sine theta cosine theta. And this expression here can be simplified using the trigonometric relationship where 2 sine theta cosine theta will be equal to sine 2 theta, where you take the sine of the double of the angle. Then if we can simplify this expression to this one, then therefore the formula for the range will be equal to your initial velocity squared times sine 2 theta all over g. So now this is your final derived equation for the maximum range, or the total displacement along the x-axis of your projectile motion. So take note of that. We already have two derived equations, which is the equation for time, where time is equal to 2v0, or the time is equal to 2 times the initial velocity in y divided by g, and then your maximum range, or your Total displacement along the x-axis is equal to initial velocity squared times sine 2 theta divided by g. Now, this g here, always take note that we already factored in the negative component of the acceleration, which is going down. So when you substitute values using these equations, you don't put any more negative in 9.8 meters per second squared. You only put 9.8 meters per second squared because you already factored in during the derivation process the that direction. Okay, so take note of that so that you will not get confused. Now, let's talk about the equation in solving for the maximum height. So derivation of the projectile maximum height, or derivation of the equation. So again, we start with a general one-dimensional kinematic equation where your Vy squared, or your final velocity, or your velocity squared, is equal to your initial velocity plus 2ay. Now, since we are still talking about, or we have factored in all of the y components. So of course, this came from, for just a reference, this came from oops, happened there. You have v squared is equal to v0 squared plus 2ax. That's where it came from. So you have just factored in that this will be the y component of your initial velocity, or the final velocity, and then will be your y component of the initial velocity, and then 2 times the acceleration times your displacement in y. Now, remember that your acceleration here is negative g. A is equal to negative g. So if you substitute that with respect to the direction of the y, then Vy squared is equal to initial velocity in y squared minus 2gy, where y here is maximum height. So the formula that we used for the range is from 0 to b, right? But for maximum height, we will only have at point A because that's where the maximum height is. So your y here, this one, will be the maximum height, or h max. And at h max, remember that the final velocity, remember, your velocity at your velocity at maximum height is 0 because it momentarily stops and then it goes down. So if this is the case, that y is your h max, and your your final velocity at h max, or your velocity at h max, is 0, then you can substitute. The equation is again v y squared is equal to v0y squared minus 2gy. So if you substitute these assumptions, then your velocity along the y-axis on its maximum height is 0, and then you have your initial velocity in y squared minus 2g, and your y is replaced with h max. Now, rearranging our equation to solve for just the h max, then of course we need to transpose that one first, which will give you negative 2g h max is equal to v0y squared. Negative, of course, because you have transposed that with a negative sign. Then, of course, you transpose that one also, then you'll get h max is equal to negative v0y squared over 2g. Then, or negative 2g, then you get to cancel the negative sign. Then this is now your equation. So h is equal to your initial velocity in y squared divided by 2g. Now going back to solving our components, we know that your initial velocity in y is equal to your initial velocity sine theta. And if that's the case, then we can replace this one. We can replace this expression to this one. Then you'll get h max, or the maximum height, is equal to your initial velocity squared times sine theta. Remember, why do we have sine squared theta? Remember that when you substitute the expression there, you'll get v0 sine theta squared. then there's a square, this one, right? So of course you can distribute that one. That will become v0 squared and then sine squared theta. Oops, this is 0. So that's why you have this equation here. What does this mean? So this means that you take the square of the sine of the angle over 2g. And also, again, I'd like to remind you that your g here will be just 9.8 meters per second squared because we already factored in the negative sign. Now, let's talk about the range and height of an object with respect to the launch angle. So it said that the range and height of the projectile is dependent on the launch angle of the projectile. So as you can see here, the furthest or the angle that will yield the farthest maximum range or maximum the farthest range will be 45 degrees. As you can see here, it has the farthest range. And you also can see here that there are angles that yield the same range. But of course, they differ in maximum height. And these angles are known as complementary angles. As you can see here, 75 degrees and 15 degrees has or have the same range while they have different heights. So complementary angles are equal, or when they are added, they make up 90 degrees. As well as you can see here, another example, 30 degrees and 60 degrees. So they are complementary angles, so they will also have the same range, but of course they will differ in height. So maximum or the angle that will yield the farthest range will be 45 degrees. The bigger the angle, the shorter the range, and the higher its maximum height. But of course, that is not, or when the bigger the angle above 45 degrees. Because as you can see here, as the angle increases from 0, of course, it also increases its range and its height. But the moment it increases more than 45 degrees, it its maximum range or its range starts to decrease. Okay, take note of that. We'll end there first. This is part 1 of the projectile motion, and we'll have another video for an example on solving problems with regards to projectile motion. So see you in another video.